Go ahead.
Okay, welcome everybody to the second session of the conference. It is good to see all of you. We will have the same format again, where the presenters for the session will give us each a short overview, and then we will hear briefly from the poster presenters. And then we'll go to the general discussion where people are asked to use the raise hand feature. So with that, let's get started. And so Licha, I believe you are first.
Okay, hello everybody, good morning or good evening or good afternoon, wherever you are. It's a pleasure to be here. So I understand that my presentation was a little bit cramped, but I realized that being a video and you can stop and start and digest at your own pace, then that could be okay. And so in the presentation I touch on two things. One in more detail, and the other one, since it's really technical and there are a lot of equations, and equations are better looked up in the privacy of your own office rather than in public, I'll just glance through it and just give you a big an overview. So the first part of the talk was about blinding for galaxy redshift surveys. So the idea is to try to blind for cosmology, of course, not for systematics. And blinding has been around for a long time and in different areas of research, science, and physics, but in large scale structure that arrived relatively late, relatively recently. And in galaxy redshift surveys, basically it has not been applied. So this is a suggestion on how to do a blinding from the map, from the actual, rather than from the summary statistic itself. And so the idea is to use only the radial, so mess around only with the radial coordinates, because in the vast majority of analysis of galaxy redshift surveys, you don't work with redshift, you always work with distances. And then to transform redshift in a distance, you have to assume a cosmology anyway to do that transformation. And then you can get that dependency, if you want, out by doing relative measurements, and you can correct for that, but still you have to do this. And so you can use that by putting an extra blind step in there to blind just the cosmology and not anything else. And then unblind when you are sure that you've done all your tests and everything checks out, and then you have disentangle the results that you're interested in with the checking procedure to make sure that everything works, which is a risk that one runs if one doesn't blind. And we tested that they work on BOSS data. And of course, the next generation survey are going to be much bigger than that, and the precision is going to be much bigger than that. So we'll have to test that on MOX first, and then if that pans out, then apply it on the data. And I highlighted that this paper was in collaboration with Samuel Bryden, which is the PhD student. This is part of his PhD, Hector Gilmarin, and Jose Luis Bernal. In the last part of the talk, which is the brief one and the one more full of equations, I mentioned something that it's even higher order correlation function, or actually in the counterpart in Fourier space. So you've heard, I'm sure already, about the 3-point or the bispectrum. And this is, we add the 1 to that, and it's the trispectrum. So this work is done with Davide Gualdi and Sergi Novel. Sergi was not even a master student when he submitted the paper. He's now a master student. Again, Hector Gilmarin. So the trispectrum must be very useful in the cosmic microwave background to constrain primordial non-Gaussianity. But in the cosmic microwave background, it's simple because it's 2D. And therefore, the number of quadrilateral you can make is still reasonable. When you go to three-dimensional galaxy surveys, then adding the extra dimension, the number of skew quadrilateral you can make now grows, and then you have to compress or to do some average. And so we resorted to what we call the I-tri spectrum, which a posteriori we realized that it was already mentioned by Sefusati, but he couldn't at that time compute the theory behind, just because the computer wouldn't allow you to do that. So he already understood you have to integrate, but now we can. And so I show you how to define the estimator, and I show you that you can measure it from dark matter only and body simulation and get some meaningful number out, and then there is some extra information in there just out of Fisher. But between this and applying to real data, there's still quite a lot of work to do. I mean, this is still spherical cows, and we need to go beyond that. But first start with spherical cows and then go to the next level. I'll stop here.
Okay. Thank you very much. So it looks like next we go to Jaime.
Right. So hi, everyone. Welcome to my home. This is Bogota, Colombia. This is one of the nice things you can do now. So I will summarize my talk by sharing a few of the slides, actually. So this has to do with the cosmic web. On the left, you have real data. On the right, you have simulations. And the goal was training the computer to find those filaments and voids. I've been exploring in the last decade a lot of algorithms to do that in simulations or when you have densely sampled data. But we wanted to develop new algorithms to work on galaxy survey data, meaning that you only have a few points to sample the cosmic web. So, and what I explained in the video is why we picked an algorithm called the beta skeleton from the community doing computational topology. And this is how it looks like, actually. Here on the right, here is the graph once it's built. And here is on the left is the classification we are doing with kind of this algorithm working on the dark matter particle data from the simulation. This is Illustris, as I explained in the video. So what have we been doing with this beta skeleton? So the first thing was just, of course, compute some simple statistics, the length of the edges, the number of connections. Very quickly, we realized that once you have edges, you can try to perform Alcock-Paczynski tests. So this is something I mentioned in the video. Something else we have been doing is trying to predict this tidal web, this dark matter density web from the beta skeleton. This is a summary plot of how it looks like if you're trying to make the confusion matrix. In the video, I explain how we use the random forest. And I explained that it does a good job with the peaks, the filaments, and the sheets. It's very bad with voids. Probably you know why already if you saw the video. So if you haven't, I encourage you to see the video. Given that it's very bad with voids, we developed on the side another void finder using the beta skeleton, which later our hope is to use that with new data from DESI that it will be coming in the few years. One problem that we had once we have this beta skeleton is that we want to have an easy way, for instance, to compare the beta skeleton from real data and the beta skeleton from mock data. And playing with that, we developed a summary statistic. So we went from graph theory to information theory. So we defined the entropy from the probabilities of having n connections, the connectivity of this graph. And it is successful, at least in differentiating, finding the difference between clustered and random points. But then thinking a bit more about the problem, the proper way to compare these two different probability distributions is actually what will be called the Jensen-Shannon divergence between these two distributions related to the entropy. In the video, I show actually how this complexity has been useful. For instance, we build the complexity on both data, on different types of mocks. And at the end, the important thing is that we are getting the information on how good is your biasing model by comparing this complexity, this summary statistic built from the graph, which is built from the observational data. And quickly, the summary was that this beta skeleton, this graph, is a kind of a new tool to describe the large scale structure, not new in the context of computational topology. It's a very old graph, but it's new in this context of large scale structure. It has a potential because we have edges and angles to be used as an Alcock-Paczynski cosmological test. Then we are also able to apply it to our original goal of finding peaks, filaments, and sheets. And then on the side, we developed a void finder based on the beta skeleton as well. And it also provides a natural way to measure what we call the entropy and the complexity of the cosmic web, useful to quantify actually how are you doing with galaxy bias in your models when you're trying to compare that very quickly against observations. And that's it.
Okay. Thank you very much. And so this session has just the two talks. So now we'll go to the posters. So Mark?
Let's see. Hi, I guess I'm trying to share my screen, but
for the posters, we are preferring not to just
no,
tell the posters.
Oh, sorry. Yeah, right. So my name is Mark Nierink. My talk is about, or my poster talk is about filaments spinning generally in the cosmic web, and I guess that's a good enough summary.
Okay, John?
John Suarez couldn't make it. He's a graduate student of mine,
Okay.
but his poster was on the part I was showing on machine learning to connect the beta skeleton to the tidal web. So that was his poster.
Okay, very good. And Karima? Karima, are you online?
I don't see her.
Don't see her. Okay. And David?
Hello everyone, thank you for the space. Galaxy usually at one measuring level may be unobserved or untargeted due to the various observing condition problems, or more importantly, due to the fiber collisions in the instrument focal plane. The main objective in our work is to show how it's possible to recover the correlation function for bright galaxies in the samples of galaxies using mitigation techniques with a simulated catalog for the measurements taken with the DESI telescope. Thank you.
Okay, so thank you very much. So now we will go to the discussion, and if you have a question or comment, feel free to use the raise hand feature in Zoom.
So I cannot raise my hand because I'm the host, but I have a question to Licia. So Licia, in DES, we do have blinding procedures, and maybe it's related to what you have suggested. We do it at the level of 2-point correlation functions, changing the cosmological parameters. But one thing that's important is not to mess around with the chi-square fits. Because if you measure, the idea is to have the analysis such that the chi-square is trustable, even when you go with the real data. So my question is, in your proposal, you also keep the chi-square fixed, or it doesn't change much?
Yeah, excellent question. So yes, the blinding at the summary statistic level was also discussed, and it's also a way to go. So that's the way the DES went. And so what we wanted to do was basically to avoid having, which maybe doesn't happen for survey that don't have spectroscopy as a heavy component, to have people compute the summary statistics because they need to check some systematic from the summary statistics, but do cosmology at the same time, and then blind that a posteriori. So we wanted to avoid that. But definitely, it's just an organizational question. If you can organize yourself to blind the summary statistics, that's fine. And there are other way of, for example, blinding at the likelihood level, where you mess around only a tiny amount with the covariance matrix, but in a coordinate and coherent way, and you bias your results in a controlled way. So this is by Salentin and collaborators. So yes, the chi-square was one of the first questions. So if you blind and your chi-square go completely berserk, it makes no sense to blind. So so the way in Galaxy Redshift surveys you do your chi-square is you calibrate the covariance matrix on a suite of simulations, and you need to do that for a fiducial cosmology anyway. So the way you do it, you make sure that the correlation function of the simulation matches the correlation function of the observation. So in principle, you could decide to just match the simulation that match the blind data. It turns out that there's not much difference. So if you blind at the 2 to 3 sigma level, or even for some parameter, you can blind even more, then this is not such a big deal. Remember that it's not like in the CMB that the covariance matrix in the likelihood changes as a function of the parameter to keep track of the cosmic variance. You just keep it fixed and assume a Gaussian likelihood, which, you're making two mistakes, but they compensate each other. So what comes out is not that bad at the end of the day, and you can calibrate that on simulation. So we did a whole suite of tests. It's probably in the extra slide that you didn't see in the video, but if you click on the PDF, they're probably there, on making sure that the distribution of the chi-square on the blind data, it's reasonable, and you can't unblind just by looking at the chi-square. Yes, but that is an important point.
Thank you, Hideki.
Okay, and it looks like we have a question from Miguel.
Yes, hi. Sorry, all the co-hosts cannot raise hands, so we cannot follow our own protocols. We have to find the way around that. No, I did it in chat. Anyway, I have a question also for Licia, so which is regarding the blinding of data. So you said that you decided to blind only along the line of sight, right? And it's related to what Rogerio is saying, because if you blind the data in a way, for instance, which is anisotropic, it will affect your chi-square, but it will allow for going beyond lambda CDM in a more robust way, which means going beyond homogeneity isotropy. I'm trying to understand, did you ensure that your blinding had to be kind of isotropic, or it could be completely anisotropic?
Okay, so the way you can blind within lambda CDM, and you can blind away from lambda CDM, and that's exclusively under your control, as long as you don't tell the rest of the collaboration what you've done, right? So you can blind within lambda CDM by simply saying, well, let me shift my cosmology in such a way that if I had originally a lambda CDM, which I don't know if I have, that's what the universe decides, I'm going to end up with a lambda CDM with different value of a parameter. For example, say that you want to change omega matter by a certain amount. And then you do this redshift to distance conversion by using a cosmology which is not your fiducial cosmology, or in this case is not Planck. And then you come back a little bit, and then you say, I use this fiducial cosmology, which is not the one you say you use, right? And then whoever does the analysis can decide to use the same fiducial cosmology or another one, because it's the fiducial, it doesn't matter which fiducial cosmology you use to do your analysis. But by now, they don't know what the real cosmology is, because you've shifted stuff. And you shifted both in a like AP-like way. So you change the Alko-Paczynski, and then the other change is a Ricci space distortion. So you change F sigma 8. But, which again, it's only a line of sight thing. So we could have also changed the things on the plane of the sky. But if you have a photometric input catalog and then you change the position, then it's obvious that you're blind. And then people can go and say, that's what you did. Because you're not going to change the position also the photometric catalog. So the photometric input remains the same. People can correlate and don't realize,
Angles you cannot change, but the conversion from angles to Fourier modes, that depends on cosmology and on mu and stuff like this, right?
Exactly.
So my question is to you, in the blind you did, in the end, how general was it? Was it within lambda CDM?
You can blind away from lambda CDM if you want, yes. So you can blind for whatever expansion history you want and for whatever growth history you want, and they don't have to match each other under GR either. So I could even make you believe that it's not GR.
Right. It doesn't. So the only thing you were worried about is that if you change the angles, you would change the weights, right? If you're doing, I'm worried if you change something in the pipeline. That's what I'm saying. Some astrophysical assumption.
Yeah. So I don't want to mess around with the weights because those are systematic weights, and you don't want to blind the systematics. You want to have access to the systematics. You only want to blind for cosmology. Yeah. But yes.
Okay, and I see Oliver next.
Yeah, hi, Licia. One more question about the blinding, actually. I think I've witnessed it at least 2 times now that an analysis was unblinded, and then relatively quickly it was clear that something was wrong. And then basically, if you follow the kind of the code of honor, then you publish it anyway, and then you are really transparent and document what changes you did after unblinding. And to me, sometimes it feels like almost this is just shifting the problem to the next layer. So now the confirmation bias of the entire community can kick in, basically. And I sometimes think a blinding strategy is only as good as the set of tests of blind tests that you come up with beforehand. And is there some sort of, like, what are the crucial things that you would think one would need to make sure before unblinding?
Excellent question. A priori, I cannot yet tell you because I don't think we've done enough of a detailed study to come out with what checks we need to pass before we unblind. But this is something that will have to be done and will have to be declared a priori. The thing is, I think that knowing that the results are blind will help keep you honest. So you don't go and keep checking your pipeline until the Planck result come out. You stop checking the pipeline and you go on to the next level because you know that, it doesn't necessarily have to come up like Planck. So in that sense, it helps you keep you honest and it protects you against this, server's bias, which whether you want it or not, it's sometimes even not conscious. But I agree, there will have to be a set of declared a priori tests that you have to pass before you unblind. And you can always add some more tests. And you can always decide that we are not ready to unblind, or you can always decide to, start again because you need to go back and then you blind again. But you don't unblind and then go back. Yeah. Or if you do, you have to publish what you find and say what went wrong. I totally agree.
Okay, and Jorge, I believe you are next.
Yeah, hi, Licia. So I have a question about the trispectrum estimator. It's a naive question, so sorry if the answer is obvious. It's just that I didn't understand. So when building the integrated trispectrum, so one integrates over the folding angle and the diagonal, right? So I was wondering whether this loses some information about the limit in which the diagonal goes to 0. Because there is some interesting theoretical things that can happen in this limit. So I was wondering whether I can use this estimator to look for this limit, or The microphone is off.
Okay, yes, extremely good question. So you will have to come up with a way to integrate, because otherwise you can't handle this beast. And so we come up with this angle along around the diagonal, and then the diagonal. But then if you look at the actual integral itself, it says the diagonal goes from a minimum and a maximum of the sum and difference between two k vectors. Now, this means that, so depending on how you define this min and max, there may be some squeezed things in there. So if you're only looking for squeezed configurations, so if you're looking for squeezed configuration, then you don't need to do that.
Then you
have many less modes.
Okay, so then you can just so then you can use the estimator for the full trispectrum, maybe, because you're only focusing on a subset. What do you?
Exactly.
Okay.
If you know which configuration you want to look at, by all means, go for those.
Okay.
This messes things up a little bit, but if you don't know where to start from.
Okay. Yeah, so they will be there, but you integrated over several, so it's hard to look for a behavior and stuff like that.
So again, some of those configurations may actually be confused by the unconnected part, right? So in that case, you may want to look for those configurations that have a diagonal that goes to 0 but are not unconnected. And then there are even less of those. So I would say just go for those.
Okay, thanks.
Okay, and looks like Mark, you are next.
Hi, so I have a question for Jaime about the beta skeleton. So I think it looks really cool, and I like the way that that you framed it in terms of an angle. Well, in terms of a sort of PDF with respect to angle, which seems, as you said, sensitive to redshift-based distortions and Alcock-Paczynski. I think I'm curious why you're using, well, it seems like the full shape of that is useful, and I'm not sure why you feel it necessary to condense this into a summary statistic that that distinguishes from random, and also that. Do you think that? So the question is, do you think that that full shape is theoretically predictable, and have you tried to do that?
So yeah, first of all, concerning the shape of the what we call the mu, this angle of every edge with respect to the line of sight. Yes, we have to use the full distribution to be able to do constraints on the cosmological parameter. I agree absolutely with that. We have still to calibrate that with simulations. We have not been able to provide a good derivation of the shape, which is your last question. And going through the middle of why is the summary statistic for the entropy, and the reason is that we are always using. We were first trying to compare different kind of mocks at the beginning, and then mocks against observations, but then deriving some chi-square from the mu distributions of the length distributions was very dependent on number densities, for instance, or the exact shape of the footprint, let's say. So we went to use the randoms that come themselves with the data. We have the same shape, same weight, same everything. But then we fixed that at least. And the goal of the summary statistic is that it's a summary, but it's a proper way to compare density distributions. This Jensen-Shannon divergence is the proper way to compare two distributions, not to make the difference of the two summary statistics, but the difference of the two distributions and put that into a summary, which we call the complexity. So the reason was it was simply convenience at some point that we needed to again go back to the randoms, and also because the void finding method that we use is based on randoms. So at some point we were looking at our different projects based on the beta skeleton, and we were using the randoms, and then we needed that proper way to compare two distributions. We found this Jensen-Shannon that ends up being a single scalar, but the motivation was not just what is the scalar, but what is the proper way to compare two distributions, one coming from randoms, other coming from real data.
Thanks.
Thanks, Mark.
And Rogerio, looks like your hand is raised and in the chat.
Yeah, I cannot raise
So
my
go
hand.
ahead.
Sorry. I'm a host. Okay, two quick questions. One for Jaime, another for Licia. So Jaime, well, I asked both. For Jaime, is the results are beta dependent for the beta skeletons. Looks like a friends of friends parameter, right? So how do you deal with this dependence on beta, and how do you choose beta? And the question for Licia is kind of a provocative question, because that the bispectrum is done, and then you go to trispectrum, and then the question is, when do you stop?
So what I mentioned, this beta skeleton, this beta is a real parameter, real continuous parameter, must be different than 0. And then studying the entropy, we find a good excuse to explore the influence of beta. And actually it has a minimum. If you saw the video, it has a minimum. You can understand that from graph entropy, and it happens at beta equals 2. So for many studies, we are using beta equals 2, for instance, for voids. And also for beta equals 1. Why? Because it's a special graph. It's called Gabriel's graph. It's useful because it has it's easy to interpret. It's easy to make kind of theoretical predictions if you are at beta equal 1. So for all the studies, we are using mostly beta equal 1 because it's useful analytically, and beta equals 2 because it's the minimum of the entropy. And you can see by eye what is happening. The graph is kind of the thinnest that you can be, but still keeping the connectivity around the cosmic web.
So, Rogerio, your two questions are actually very related to each other, because you could always go back to, there is a finite information content in that distribution. At what point did you extract most of the information content? But I don't think we know what the information content actually is. So if everything was Gaussian and we will see directly the dark matter, then we can quantify that, right? We know everything, we know the full statistics, we measure the power spectrum, and we are home dry. But it's not. And on top of that, it's not just that there is not just dark matter. We don't know if it's Gaussian. We know it's non-Gaussian. We know there's no dark matter, and it could be anything else that is not in a model that we have in our head. So, so in this sense, having extra tools can help you both extract extra signal that leaked away from the power spectrum, but also to constrain systematic. And by systematic, I mean anything that is beyond what you put in your model of everything. Reality, the universe, the cosmology, the instrument, bias, the galaxies, whatever. So in this particular case, so we know that for the CMB, the trispectrum was very useful for primordial non-Gaussianity. It really helped break the degeneracy beyond what the bispectrum could do. For the large-scale structure, we didn't know, so we went the Fisher way within a model. And then for the typical local non-Gaussianity, then compared to the bispectrum, this reduces the error bar on, say, FNL by 30%, reduce the error bar on GNL by some other amount. So you say, well, if you can do it, why not? Because reducing the error by 30% is like having a survey much bigger, but the moment you've seen all there is to see, because you're already covered covering, or your F-sky is basically as close as one as you can get, then you may want to bite the bullet and actually do it. There is even more than that, because we have been talking about the monopole, but in principle, there are the multiple. Like for the power spectrum, you have the monopole, the quadrupole, and the hexadecapole. For the bispectrum, you could also do the different multiples, and for the tri-spectrum too. So again, the question is, at what point do you stop? What I would argue is take a simulation that is based on lambda CDM, make sure that the more you add, the more you break the degeneracies, or you can get constraints on the possible systematics, or a handle on the systematics. And then if it's doable, why not? But the moment you will get to a point of diminishing return. And but I would like to see that point before saying this is the point of diminishing return.
Thank you, Licia. Or you can go like just modeling the whole PDF of the fluctuations.
You mean what is called the direct modeling, yeah?
I guess, yes.
Yeah, the forward modeling. The forward modeling. That's yeah, that's the other way to do forward modeling. So
I guess Virgo is going to talk about this, and Oliver talked about a little bit. Thank you.
Okay, and I think Mustapha is next.
Yeah.
Good to see you. I've not seen you in many years.
Yeah, well, good to see you, Chris. It has been a while. Yeah, good to see you. And well, my question is for Licia. And same thing, I did not see you for a while as well, Licia. So my question is a general one, and I think so. My group and other groups very often do what we now come to call data reuse. In other way, redoing cosmological analysis using data sets that are available from Planck, from large-scale structure, and so forth. And finding the best fit parameters for whether for lambda CDM or WCDM or mu sigma models, and then using, for example, this metrics or Bayesian selection, or using the DIC to see what models are preferred and so forth. We do find the results sometime in favor of lambda CDM, sometime in favor of other models. And my question then is related to, for example, blinding, or if we want to take into consideration, my question is general. So are there any further considerations that one should do in this data reanalysis to kind of, as far as blinding or catching up on things that have been done before? I would like to hear any comments from you about this.
So if you have a data set, you can blind it once. The moment you have unblinded it, if your analysis is sound, then that's it, right? So you know the answer. You already have a prior there. On the other hand, when you start combining different data sets, then you can break the degeneracies, and then you can reduce the error bars a lot. And then as you reduce the error bar, it's like basically saying, I don't know, we have BOSS, we now do DESI, then DESI cannot be blind because we already have BOSS and it's the same sky. But if the error bars are different, as long as you blind in a way that you are still consistent with the previous error bar, nobody will be able to tell. So there is some space for blinding there. The issue is, how do you blind coherently when you do this data fusion and you combine, say, lengthening with Lyman alpha, with BAO, with and I don't think that's a completely solved problem. I mean, I think it's possible to solve it, but I haven't thought about it. So yes, if the error bars get smaller, you can always blind. But if you redo the analysis on the same data set, once you unblind, you unblind.
Okay, thanks.
Okay, and Miguel?
Yeah, I have a couple more questions. So one is for Jaime. So, well, actually, two for Jaime. So, is there any relation between this beta skeleton procedure and the Voronoi tessellation procedure? Are they completely unrelated? Because it strikes me as some way similar.
So they can be related, but one graph is not a subset of the other. They can be related from the point of view of the algorithm. If you want to build one of these two, actually you kind of reuse the same tools, but otherwise mathematically they are quite different.
Could you compare me in which sense they complement each other?
For instance, if you take a look at what is the intersection between the two graphs, one is not contained into the other.
No,
one
I
has
understand.
that the other doesn't.
Mm-hmm. But you think they can be complementary in the sense of the information they...
Exactly. And for sure, the tools that you use to look around your points and do intersections of spheres that you have to do kind of in both is kind of the same, can be reused. But otherwise, it's a quite different structure. The motivation to use this algorithm, the beta skeleton, is because people using kind of, let's say, Voronoi or some other networks, they were looking for graphs that still preserve the topological structure, meaning that if you have two maxima, you're still linking these two maxima through the filament. And it's done in a much better way through the beta skeleton, for instance, than in Voronoi. In Voronoi, actually, you can estimate local densities, but it goes kind of all over the place, while the beta skeleton is kind of choosing places to go. As you increase the beta, you can actually go through the web, right? Through kind of this topological information that you are having between, let's say, two maxima or minima. Okay. So that's one of the advantages and one of the big differences between the two, actually, how you conserve topological information.
Okay, interesting. And getting a little more technical, you made a confusion matrix where you try to see if you could detect void sheets and etc. So the point is, what did you use as your true values? I mean, what was your reference values? How did you know where the voids were?
Exactly. So here the goal was going from galaxies, beta skeleton, to the web defined by the dark matter. So that was my truth, what I know from the simulations from the dark matter. That was kind of the goal. So the truth was kind of what we have been studying for the last 10 years of this tidal web concept, where you have your density, local density, you compute the gravitational potential, you compute the Hessian, you have then 3 eigenvalues, and with respect, if this is positive or negative, you can place this this location in your dark matter simulation as peak, sheet, filament, or void. So that was our truth, kind of the best well-studied dark matter cosmic web. And we want to go from the beta skeleton to that dark matter without doing any kind of reconstruction. That was also the goal, avoiding the step of doing full reconstructions or Monte Carlo or anything like that.
Okay. And I have one more question for Licia. I don't know, Chris, can I ask, or should there's more questions on the way?
Yeah, go ahead.
Okay, it's more of a long, it's for Licia now, is thinking ahead. During this COVID times, we got to read lots of medicine literature, right? And I think when you blind things in cosmology, the closest we have in medicine is the triple blind study, is what actually they are doing now. Some in medicine, they do the triple blind. And I was curious what was the triple blind. And the triple means the person doing the statistical analysis also doesn't know who is placebo, who is not, right? So that's the closest we have, I think, for the cosmologists, because I think the double blind they get for free from the universe, right? We don't have placebo. So, okay, but looking also in medicine, they also take into account, they also worried about what we call the opposite of confirmation bias, which is they call p-hacking, we call it a posteriori effects, which means that if you have a large amount of data, you're going to find outliers, right? Just statistically. So in CMP, people are worried that this since a long time because you reached cosmic variance limited since a long time ago, and people have been you're looking for, flux in the data, right? So how do you think we'll converge, as you said, if you follow this Moore law, at some point you're going to have measured most of the galaxies in the universe, And confirmation bias will no longer be our main issue, maybe, but a posteriori effects will start to be our main issue. So how do you think these two things will cooperate?
Yes. So, I mean, in principle, if you know exactly your statistics, you could do that. And then it's like in the CMB, you can do that because you can generate a lot of CMB. So within a model, you can do that. And then it turns out that for example, all the anomalies on the large scale, for example, yes, they are this 2-point-something sigma. But that's exactly why there is this golden standard of 5 sigmas, because the 2.5 sigma may happen. So you have something there, and then you do all this, Bayesian evidence when you are like, the 2-point-something level 3. The moment you get to the 5 sigma, then and that's why. So we'll end up a little bit like that.
I just had the feeling that as we move to more big data, 4 sigma and 5 sigma will start being more common, even if they are flukes anyway, right? Because just a big data.
Well, it depends what you yeah, okay. So it depends what you define by 5 sigma, right? So, for example, how do you subtract point sources from a CMB map? You look for the 5 sigma, but you know they are there. You know there are point sources. That's how you find them, right? On the other hand, if you find too many 5 sigma for the amount of data you have by 5 sigma, by knowing that probability, then you start worrying about. Like if you measure the Hubble constant 15,000 times, then sometimes it's going to be 74, some other time it's going to be 68. You're going to have a distribution. But if you measure it 2 times or 5 times, say, and it's 2 times is 74 and another 2 times is 68, and the error bars are small, then you worry. I don't know if I answer your question.
It's a very open-ended question. Let's move
on
to other people.
Okay, so Hideki.
Thank you. I have a question to Jaime. There was a question about the matrix of truth and the prediction of the 4 different structures, peaks and the filament and sheet and void. I understand the beta skeleton is sensitive to filament, but it's not sensitive to peaks, but it's a very high dense region. Why is there some reason why beta skeleton is not sensitive to the peaks, high dense region?
So the reason is something that is kind of very common to any machine learning algorithm, and is the following: is the number of samples that you have in your classification problem. So in this example, we have 4 classes, and how good the algorithm is doing its job is basically proportional to the number of examples that you have in that class. Okay. So for instance, voids was the absolutely worst. Why is that? Because you have, by definition, very few galaxies in voids. It was very good with filaments. Why? Because you have most of your galaxies are in the filaments as defined in our algorithm.
Yeah.
Peaks, you have very few peaks, but those are dense regions. That's why it's intermediate. That's why the same with sheets. So this is kind of a very generic problem when you're faced with classification algorithms with unbalanced classes. So that's basically the reason. If we actually use as truth a different cosmic web finder with different balances between the classes, it's the same thing. We do best with the most represented class, and we do worst with the worst represented class. So that's basically the reason, the unbalanced nature of the problem.
Okay. So can I add one more question?
Go ahead.
Yeah. So if it depends on the kind of setup of the simulation or something. If you add, for example, if you apply this beta skeleton to a very, high resolution simulations with a big number of particles in it, is this sensitive to, still not sensitive to the peak, or it is sensitive to peak?
So if you are trying to find the cosmic web, in the sense of having as truth this cosmic web defined by the tidal tensor, then yes, you do a much better job if you have more a denser survey, a denser set of points. But on the other hand, if you are just simply trying to compare, for instance, that's one of the applications that we're exploring, real data and mock catalogs to see whether you are doing bad or good with your biasing model. If you use the complexity that I showed, this is independent on the number density. So that's why also we are exploring that way, because it's independent of the number density. But then yes, if you go this cosmic web, then yes, it depends strongly on the number density of points. If your goal is comparing some other properties like galaxy bias through the complexity, then you're fine.
Okay, thank you.
Okay, and Nicola?
Yeah, hello. I also have a question on the beta skeleton. It's very interesting, and it seems like a very powerful way to say which galaxies are in a given structure, like filaments or let's say cluster. But it does that based on, let's say, galaxies in filaments based on how connected they are among them. So what it actually traces is the connection among the galaxies, which is not what corresponds to the cosmic structures called filaments, which are much larger than the connections among galaxies where galaxies are embedded. So do you have plans to update the beta skeleton algorithm or formalism to be able to also trace the large scale structures themselves in a more similar way to what is done, for example, by the tidal skeleton, which gives you also where the filaments are and so on? Or can you comment, please?
So yes, we do have plans. We do have some implementation of that, in the sense that it's similar with the tidal web. What we did, of course, we define locally a point belongs to one of the 4 classes. And we did at the time was, for instance, a friend of these points classified as filaments, and then this becomes a filament, the object. With the beta skeleton, you can do something similar. You can keep the group of points that were classified as, I don't know, peak or filament. You can do that, it's doable. But one more thing that you can do actually is to increase your value of beta. And this starts to break the connections, and you end up with entities like more planar entities, more filamentary entities, more spherical entities. So you are guessing those are more cluster-like, filament-like, sheet-like properties. And we do that actually by tuning a little bit this beta actually to be around 2. We found this by the analysis of the entropy, and what is happening, this is the minimum because the density distribution is the narrowest one, actually. This is what is happening, kind of the definition of entropy. Low entropy, big entropy. And what is happening in this case is that you break up the graph that was fully connected, now is not fully connected, and you end up with these separate entities, filaments, sheets, or more cluster-like. For the voids, you have to do something different. We do something different because by definition, you don't have anything in the voids, almost, very few galaxies. So long answer, but yes, we can do that, and we are doing that. It's not published, but we are doing that. We are using it. Thanks, Nicola.
Okay, Miguel, did you have another question?
Yeah, I have another question for Mark on the spin filaments, the spin of filaments. So I guess if your filaments are spinning, this will introduce some kind of redshift space distortion, right? How is this connected to the Kaiser effect, the finger of God? I mean, how do you? I'm trying to find out in the scales which would be relevant, or if at all.
Right. So we looked at relatively small scales. Not we didn't. As far as I know, there wouldn't be a Kaiser effect contribution to this, but definitely, yes. So the way that you could detect this rotating filament, at least one way that we thought of is to look at the redshift space distortions. So if you had a cylinder, a filament that was rotating in the plane of the sky, for example, one edge of it would be blue shifted and one edge would be red shifted on average. So that's what we were thinking as a way to detect it from galaxies, and how redshift space distortions would be crucial for this.
And how significant you think it will be, these measurements?
Well, we haven't actually done like for this, you almost have to do a full mock observation, and we haven't done that. But and also there's the possibility that even in real space you could get some structures that are tilted in redshift space, or in real space. I mean, you wouldn't necessarily get this just because of the redshift space distortions. You could have this on sometimes in the cosmic web anyway. But yeah, that's a great question. They say we think there could be some cosmology dependence to this, to the amount of spinning. So it's of course the velocity field, and if and so that it's sort of a similar kind of dependence. We hope to things like redshift space, things like fingers of God, where if you have a higher F sigma 8 or something, you might get more rotation in these filaments. But on the other hand, the whole cosmic web changes with these parameters, so it's a complicated thing. Thanks for the question.
Okay, and then I think the last question of the session goes to Mehdi.
Hi, my question is for Jamie, and he mentioned that we cannot classify voids and filaments because there is an imbalance in the data. So I was wondering if we can account for the imbalance by weighting each sample appropriately, or is that not feasible because we don't know in advance what percentage of the data sample belongs to the category of, like, for instance, voids versus halos?
Is more the latter, that I didn't want to put by hand what we know, of course, in the weighting, but we did what you suggest, actually, of weighting, for instance, the voids. But there, it is really problematic in the sense that basically, if we want to augment the data, it's not simply by weighting. We have to avoid the data by using more data, more examples of what a point near a void looks like, because the weights didn't help, actually.
Thank you.
Thank you, Mehdi.
All right, so we have reached the end of the hour. So let us thank all of our presenters again. And I will turn this back to the organizers.
I don't have much to say, so thank you, everybody, and see you tomorrow.
Thanks, everyone. See you guys tomorrow.
Thanks, everybody. Thank you. Bye.